Okay, so going to continue the discussion on memory management. I wanted to make a few announcements because there was no discussion on Friday. As I mentioned last week and also sent an email, there is a lab out. So please start soon. Don't wait until the last minute. The first discussion for the lab will be this Friday. Okay, but that's an entire week, a little over a week since the lab came out. So don't wait until the discussion to start on the lab. Somewhat straightforward lab, producer consumer problem with threading. I'm going to discuss or give a quick overview of the lab at the end of today's class just to get all of you started on it. Okay, so just keep that in mind, get started soon. That way you won't have time pressure when time comes to submit it. Okay, due November 4th. Okay, it's not a lot of time, but you still have a little over 2 weeks since it came out. Okay, so I'm going to continue our discussion from where we left off last time. The class attendance is fluctuating, so please keep up. If you did not come to class for some reason, the lectures, video is available, slides are available on the web page. So go take a look and try to keep up. This is a quick recap of what we have been talking about. Last time we talked about demand paging. Okay? So that takes the paging scheme for memory management and enhances it by saying you don't need to keep all of the pages of the process in RAM at all times. So this is the picture to keep in mind. This is a process. It's partitioned into pages. Okay, pages are of fixed size. There's a page table. Okay, but now not all of these pages of the process will be in RAM. Some subset of the pages will be in RAM and the rest of them will be on disk. Okay, so you will fetch pages into memory on demand. So what this allows you to do is to allocate much less memory to a process than it would need if the entire process was in RAM. Okay? And the 90-10 rule is basically what makes this work, since most of the time a process, 90% of the time a process works on 10% of its memory or pages. You only need to keep a small fraction of those pages in memory. The rest of it can be on disk and you can fetch them on demand. Okay, so whenever you access a page, you are going to look at the page table. Okay, the page table will tell you if the page is on disk or in memory. If it's in memory, you're done. If it's on disk, you have a page fault. Okay, page fault requires a disk I/O to fetch that page from disk into memory. Okay, I talked about this notion of a swap space, which is the partition or the space on disk where you are going to keep process pages. Okay, typically, you may have a separate partition for swap space, or you may have a swap file in your file system itself that the OS maintains. Okay. This is where the pages of active processes are stored and fetched on demand. Okay, we did some analysis to figure out what is the impact of a page fault, and basic takeaway was, since disk is several orders of magnitude slower. Okay, memory access times are in nanoseconds or tens or hundreds of nanoseconds. Disk access times are on milliseconds. Okay, so there's a big difference when you have nanosecond storage versus or memory versus millisecond storage. Okay, significant slowdown if you have to go to disk frequently. Okay. So we said even for an overall 10% slowdown, you can't afford to have too frequent page fault. A page fault every millions of instructions is about as much you can sustain to have even a small 10% slowdown due to the fact that occasionally you have to go to disk. Okay? So keep that in mind. Now again, because of locality of reference, which basically means process is typically going to access the same page or pages nearby in the future. Because of this locality feature, you can get away by keeping most of a small subset of pages and not have frequent page fault. Okay? That's a quick recap of demand page virtual memory. Okay, I'm going to continue from that point on. Let me pause if there are any questions on this. We'll build directly from where we left off last time. Any questions here? Okay, so today what we will do is, broadly speaking, we'll talk about memory allocation inside a process and then memory allocation across processes. What does the OS do when there is a page fault? A new page comes in, some page has to go out. Okay, we'll look at how that is done. That's basically this page replacement algorithms. Algorithms to decide how to replace pages. We'll look at several implementation issues. We'll look at one particular page replacement algorithm, look at what support do you need to implement this memory management scheme efficiently. Rather page replacement scheme efficiently, talk about some hardware support, and then the last bullet will be memory allocation across processes. Okay, you have, let's say, 4 gigabytes of RAM. How does the OS decide how much RAM to give to each process? On what basis is that done? Okay, so that's what we'll talk about at the very end. I'm not sure we'll finish all of that. We'll do as much as we can because I do want to spend some time at the end talking about the lab, okay, just to get all of you started. Okay, so some leftover slides from last time. So we were talking about demand paging. Okay, and I mentioned that you now have a page table where the page table indicates if the page is in memory or on disk. The page table, like before, is going to be stored in memory. It's a large data structure. You can't keep it in registers. You'll keep it in kernel address space. Okay? But because any memory access requires you to first access the page table, you don't want significant slowdown. So you're going to keep a cache where the page table entries will be stored. Okay? What this slide is showing is how are you going to manage the cache in software. You can either manage it in hardware or you can manage it in software. So this is basically showing you what happens when a page fault occurs. What does the OS do? So if basically the page is in memory, then there is nothing much to do. You will basically just see if the page is in the TLB. If it's not in the TLB, then you have to get it from the page table. Okay, that's a TLB miss. So if you have a TLB miss, you are going to see if the page is in memory. If it's in memory, you will basically get the page table entry and update the TLB. This is not a page fault. This is simply a TLB miss. You're simply bringing that entry from the page table into the cache. So for subsequent accesses, you don't have to go to a memory page table. Now, if the entry is not in the TLB and the page is not even in memory, that's a page fault. That basically says the page is on disk. Okay, so now what you got to do is basically go and fetch it from the disk. Okay, invalidate the TLB entry. Okay. Then basically you are going to service the page fault. That's a trap that is going to cause the OS to run. It will fetch the page. The page will be brought into memory. Okay. Page table will then be updated. As the page table is updated, you get the page table entry, you bring it into the TLB. Okay, so the page is fetched from disk into memory. The TLB entry is fetched from the page table into the TLB, okay, or rather the page table entry. Okay, and then you restart the process. Okay. So a lot of bookkeeping to be done. Okay, depending on the page is in memory and the entry is in TLB, that's the common, hopefully the common case, everything is fast. If the page is not in memory, or rather the TLB entry is a miss, but the page is in memory, you simply update the TLB. Okay, there's nothing to do, the page is already there. If neither of those two or both of those two become misses, the page is fetched from this, the entry is fetched from the page table and put into the TLB. Okay, so depending on what scenario you have, there is increasingly more work the OS will have to do. Okay. Now keep in mind that all of this is still transparent to the process. By user we mean a process. The process doesn't know that there is paging going on or there is page faults being handled. The process is simply executing instructions. Simply by virtue of having instructions that access memory addresses, some of these operations may be triggered depending on whether there's a TLB miss or a page fault. Yeah, but it's all done transparently. Now, because it is all transparent to the process, you want to make sure that certain corner cases or special cases are handled well. And these are cases where the instruction modifies some state of the process and also triggers a page fault. Okay, so I'll give you two examples of these instructions. So this is the first example, which is a very simple assembly instruction. It says move A R10. That basically says increment this register value and store that register value at that memory address. You're simply moving a register, incrementing the register and moving it into that memory address. Okay. Now let's take the case where the CPU is actually executing the instruction. It will first go and increment the register. Okay. Then it will try to basically figure out where is this memory address. Okay, what page is it in, and try to move this register value into that memory address. Let's say that's an integer. You're simply moving the register into that memory address where the integer is stored. Now, if that is a page fault, okay, if the page where A is stored is not in memory, you have a page fault. You'll have to go fetch the page in memory before you can move that register there. Okay, that's basically what the instruction is doing. But what happens typically when there is a page fault is you suspend execution of the process. You bring the page in memory and you will restart the execution of the instruction. You can't have a half-done instruction that the other half is going to be executed after the page fault. What this means is after the page fault, you are going to have to re-execute the entire instruction. Okay, because the way CPU works is you cannot execute half an instruction. You execute the whole instruction again. Okay? But if you execute the whole instruction again, what you will do again is go increment the register and then move that register to A. This time that will succeed, but you will notice that you have incremented the register twice. Okay, the first time you try to execute the instruction, you incremented R10 and then try to move it to A, but then there was a page fault. Okay. So then you service the page fault, you come back to the process and you try to re-execute. So you can't have the instruction execute when it executes twice, increment the register twice. Okay. So what that basically says is if there is a page fault, you need to unwind anything that the instruction has done, roll back so that when you re-execute, you start from where you left off. Okay. You can't have a scenario where you do this part twice because of the page fault. Okay. This instruction is easy to roll back. You're simply going to read whatever you incremented, you decrement, and you're back to where you were. And next time you execute, you'll just do the right thing. But you have to keep this in mind. If the instruction has hit a page fault somewhere during its execution, anything that the instruction may have done has to be undone. So when you re-execute, you start from where you left off. Okay. This is a simple case where you can actually unwind what the instruction is doing. I'll show you a little more difficult case where it may not be easy to unwind. Okay, there are assembly instructions on CPUs that allow you to do block copies of memory. Okay. Block copy simply says take this region of memory and then copy it here. Okay. So you are basically going to take a region and you'll copy it somewhere. This is an overlapping copy. It doesn't matter whether it's overlapping or not. Let's say you have a chunk of memory and in one assembly instruction you say start address, end address. Copy all the bytes in that range to another location in memory. Okay, so you will basically go and copy it there. Okay. Now if you have overlapping regions, okay, what you have simply done is you may start copying some of this somewhere else. Okay, and that region can be of arbitrary size. It can span multiple pages. Okay. Let's say some of those initial pages are in memory, but then somewhere in the middle, you are going to hit a page fault. Okay. Now you got to go service the page fault, bring the page in memory. But this copying, you cannot unwind. You already overwrote some piece of memory. You can't get it back. Whatever was there is gone. You overwritten it because of this block copy. Okay. The source has overwritten the destination pages. So you cannot just say, I'm going to bring that back because you overwrote it. You didn't save it anywhere. Okay. So this is an example of an instruction where you are not going to be able to unwind whatever you did. Once you overwrite something, you can't figure out what was there before, so you can't restore it. Okay. If you increment a register, you can decrement it and get it back to where it was. If you just overwrote something, even a register, let's say, you can't figure out what was there because typically you will not save that state. So unwinding state is non-trivial. Okay. So in this case, you cannot have a page fault occurring in the middle of the execution. The only way, because you cannot actually unwind this instruction, what you have to do is you have to look at all the pages this instruction will touch before you do anything, before you even start executing the instruction. So if all of those pages are resident, then you execute the instruction. Okay. If some subset of the pages are not in memory, then you first service those page faults and then execute the instruction, because this is some side effect that you are not going to be able to unwind. Okay. So what the takeaway is, page faults look straightforward. If you always said is, if you touch a memory address where the page is not in resident in memory, go fetch it from disk and restart. Okay. But there are cases like this where the instruction that you have caused the page fault maybe modifying state, and then re-executing the state shouldn't cause some problems, or you need to always restore where the instruction was before you started it and then re-execute, and that may not always be trivial. Okay, so these are all additional subtleties you have to keep in mind. Yes.
So for the block copy, it's possible that like not all of the pages involved will fit in memory.
Yes. If you have block copy scenario where not all of the pages will fit in memory, that's an interesting case. Typically, that kind of instruction you will not be able to execute. Okay, so I'm sure that the beginning and the end range has to be such that it has to be at least the size of RAM. If you have a gigantic process where its virtual address space is bigger than RAM and you're copying memory that exceeds size of RAM, that kind of instruction will typically not work. Okay, there are other questions here? Okay, so those were some subtle things to keep in mind as far as paging or demand paging is concerned. What we are going to do for the rest of this class is a much more straightforward technique called page replacement. Okay, so now suppose you have had a page fault. The OS is fetching a page from disk into RAM. Okay? Page replacement simply says, where do you put it in RAM? Okay? We'll assume that, let's say, RAM is full. There's something already resident. So to bring a page, you have to evict a page. You have to throw something out. Okay? So you have to replace one page with another. Incoming page is going to replace some page that's already present in RAM. Page replacement algorithm decides what is the page that is going to get thrown out. Okay? And it's an important decision. Okay? You'll say, why does it matter? Why don't we just put the page somewhere? Does it really matter what page is actually replaced? And you will see that it does indeed matter, because if you make some incorrect decision, you will increase the number of page faults. Okay? The worst possible case is you replace a page that is accessed by the next instruction. Not the current one, but the next one. So instruction 1 caused a page fault. You brought a page, but you evicted a page that is immediately going to get accessed by instruction 2. Okay, now you have another page fault. Perhaps if you had replaced some other page, this instruction would not have had a page fault, and you would have postponed this page fault to some later instruction. Okay. And since faults are events that you want to avoid as much as possible, they slow down your performance tremendously, you want to make this decision carefully. Okay. In some sense, you want to throw out pages that will reduce the overall number of page faults or defer them as much as possible. Okay. This is why we are going to study algorithms that worry about what page to replace at all. Okay. This is why it's an important problem for the OS to think about. Okay. We'll look at 3 different policies. Okay. The first one, like many other things we have looked at, is going to be very simple. It's FIFO. First in, first out. Okay, when page comes in, you throw out the oldest page. Okay, the page that came in first is the one that's thrown out. Okay, yes.
Did you say that if you easily throw out pages access frequently, doesn't that, but like if it's the oldest one there, does it not get refreshed each time you access it?
Okay, so you are asking what is the meaning of an oldest page? Does it not get refreshed? So oldest page by definition is the page that came in first. So you'd look at all the pages that are in memory. You see what are the times at which they were fetched from disk. The oldest page is the one that has been around the longest. Okay? It has nothing to do when the page was accessed. Okay? That is what LRU will do. Okay? This is simply saying throughout the oldest page. It doesn't matter when the pages were accessed. You're simply looking at age of the page. Age of the page is the time at which they were brought in. The current time minus the time the page was brought. That's the age. How long has it been in memory? There's been a page that's been in memory for 1 hour, and all other pages have been bought more recently. That's the oldest page. It says nothing about when the access happened. Okay? So that's an important distinction we look at just in a minute. Okay? So that's the first in, first out policy. Okay? The next policy is what is called an optimal policy. It's called min. I'm not quite sure why it's called min. It tries to minimize page fault time. Okay? So this policy says evict the page that is going to not be accessed for the most time in the future. Okay? So if you could peek into the future and see of all the pages you have, when are each of these pages accessed next? Okay? Maybe you have 3 pages. Okay? Page A, B, C. A is accessed 2 instructions from now. B is accessed 10 instructions from now. And C is accessed 100 instructions from now. Right? So the one that is accessed the farthest in the future is C, because C is going to be accessed many, many instructions later. Okay, so if you want to defer page faults, you're going to throw out C. Okay, by throwing out C, you're deferred the page fault by 100 instructions. If you threw out A or B, you would have deferred the next page fault to either 10 or whatever, 20 instructions. Okay. So what this says is look into the future and throw out the page that's accessed farthest into the future. And you can prove that this is an optimal policy if your goal is to minimize the number of page faults. And you can, I'm not going to prove it, but you can intuitively see why. Okay. You are postponing page faults as much as possible. Okay. You're throwing the page out that's going to be accessed the farthest in the future. No other page could have been thrown out that will have any page fault further into the future, because this is the farthest one. Yes.
How do you know that a page will be accessed like for this?
Okay, so question is, that's a good question. The question is, how do you know that the page is going to be accessed farthest into the future? Okay, that part I did not mention. Okay, so this policy is optimal, but it is like shortest job first. It's one of those things where you need to actually know what's going to happen in the future. Okay? Nobody is actually going to tell you what's going to happen in the future. Okay, you can't predict the future. But the point is, if you knew the future, if you knew exactly what was going to happen in the future, this policy would be optimal. Right? Just as in shortest job first, if you knew the job lengths, you could pick the shortest job and minimize waiting times. Okay? But you don't know the job lengths in shortest job first. Same thing, you don't know what the access pattern in the future is. How do you know what the application is going to do in the future? Okay? Even the application may not know. It may depend on user input. User may click the mouse and something may happen. So you don't know what code is going to be executed. So let alone what pages are going to be accessed. Okay? So this is an optimal policy, but not a practical. It's not going to actually give you anything practical. But it's optimal. You can do no better, and we'll see examples of this. Okay? So that's why there's a problem question. And the problem is you can never implement this policy, okay, because you don't know the future. The applications may themselves not know the future. Okay? So then the question is, just as when we said shortest job first is good, but you cannot implement it, can you come up with an approximation? We'll do the same thing. Okay? This main policy is optimal. Okay? It is going to minimize the number of page faults in the system, but it's not practical, okay? Which means you cannot implement it. How can we approximate it? Okay? So that's what LRU will do, okay? Least recently used policy. So it's an approximation of min. Okay? What it basically does is saying we cannot really know the future, okay? But we'll assume that a recent past, okay, is a good predictor of the recent near future. Okay? If you look at what the process has been doing in the near past, that may be a good indicator of what it is going to do next. Okay? And this is because of locality of reference. We said that, let's say you are sitting in a loop, okay, and executing the loop. The first time you go through the loop, you access some variables and you touch some pages. Next time around, you may access the same variables, or if it's an array, you may be offset by 1, but similar set of pages will be accessed. Okay? So if you look at the past, and the past is always known. Past is deterministic, it's already happened. Future cannot be predicted, but you do know the past. Okay, so if you look at the past and says those are the pages that the process touched, and that may exactly what may happen in the near future. Okay? So if you make this assumption that the near past is a predictor of the future, or rather the near past is the predictor of the near future, then you can approximate min by saying I'm going to look at the past and just assume that that's what the future is going to look like, and I'm going to throw out the page that's accessed farthest in the future, which essentially, looking at the past, says I'm going to throw out the page that was accessed the farthest in time in the past. Okay? So you have to understand that this is the difference between LRU and FIFO. Okay? FIFO says throw out the oldest page, the page that was fetched first from disk. LRU says throw out the page that was accessed much in the past, not necessarily fetched, accessed. Okay? You could have fetched a page and you could still be accessing now. You could have fetched it 1 hour ago, but if it's accessed recently, then you don't throw it out. Yes, question.
Does this algorithm start once the system is started, or does it keep track of the history going?
Yes, the question is, how do you keep track of history? You do have to keep history here. Clearly, the past is going to tell you what to do, we'll see how to implement LRU. How do you keep track of this history? What are the implementation issues? Because this is what FIFO is actually not necessarily the most sophisticated one to use. Min is not practical, so this is what most OSs will implement. So we'll talk about implementation in a little bit, but you do have to keep the history in mind. Okay, how do you track this history efficiently? Then we'll look at in just a few slides. Okay? But these are the three policies to keep in mind. We'll run through some examples. Okay? FIFO, throughout the oldest page. Min, look in the future, throughout the one that's accessed most in the future. LRU, say look at the past, throughout the page that was accessed the farthest in the past. Okay? Assuming that's the future, that will reflect what might happen in the future as well. Okay? So we'll start with FIFO. Okay? So we'll assume your memory has only 3 frames. Okay? The memory is sort of 3 pages in size, very simple system. And we'll assume that there's a process running. It has 4 pages, A, B, C, D. Okay? And this is the way pages are accessed by instruction. Okay? That's what's referred to as a reference stream. So instructions that are executing are accessing pages in that order. This is what the execution of the process looks like in terms of pages it's going to touch. Okay? So then the question is, if that is what the process is doing and you have 3 frames to use for this process, then how does the memory look at any point in time? Which of the page accesses are page faults and which ones are not? Okay? So this is basically for FIFO. We'll now basically fill the memory up and see what happens with each page access. Okay? So the first page access is A. You start with empty memory. Is on-demand paging. Okay, so this is A. Memory is empty. That's a page fault. Okay, you're going to fetch page A from this, and let's say you put it in frame A. Okay, so I'm going to write this here. So first up is A. Okay, that's a page fault, so I'm going to mark that with a star. Okay. Next, you access page B. Okay, so A is still in memory. Okay, so that's a page fault because B is not in memory. Okay. You fetch B from disk and you put it in the second frame. That's a page fault also. Okay. You access C, same thing. Okay. So now you filled up memory. Okay. There are 3 frames, you filled up 3 pages. Okay. So next access is A. Okay. So that's not page fault because A is already in memory. Okay. Then you access B, not a page fault. B is also in memory. Okay. So these 2 accesses are not page fault. Then you access D. Okay. Now D is not in memory. You only have A, B, and C. So that's a page fault. So now you are going to fetch D. Okay. This is where page replacement is going to come in because memory is full. There are 3 frames. You have 3 pages. So you need to throw something out. Okay. Now FIFO is going to say throw out the page that was brought in first, the oldest page. Okay, which one is it? It's A, that's the one you fetched first. So FIFO is simply going to throw out A. So there are 2 of these. So you simply throw out A and bring D in. Okay, so now memory looks like D, B, and C. Okay, so then you access A again. You just threw it out. Okay, out of luck.
B, C, and then D because D was the.
Sorry, what's the question?
Would it be B, C, and then D? With D be last?
B, C, and D.
Yeah.
Meaning what?
Since B is going to be the next one to be out, right?
Right. Right now we are here.
I mean, the next one is B. This is going to be the first one.
He's saying that you would lift up, once you evicted A, you would lift B up, C up.
Oh,
and
no,
put
no,
A,
no.
B
So
in.
this is not an ordered list. This is frames on memory. This is page 1 in RAM, page 2 in RAM. Okay, this is not telling you in what order. This is not sorted. This is simply, there is a location here, you just brought it and overrode that location. This is another memory location. This is so it's not, memory is not sorted. Memory is simply a sequence of pages. Okay, so you evicted the first frame. Okay, so this is frames 1, frame 2, frame 3. Okay, so this is not kept in any sorted order. This is simply saying, think of this as RAM. Okay, there are these 3 locations, so you can replace one of these 3. Okay, but you don't sort it. That is a separate data structure that will keep track of when it was brought in. Okay, so we are not sorting it. Yes.
So in practice, there would be a queue somewhere that would be keeping track of which pages.
Yes. So in practice, you will have some additional data structure in the OS that may keep a linked list saying this is the order in which you brought in, or for each page you may have a timestamp. Okay, basically what you will have to have is a timestamp that tells you the age of the page, and you compare timestamp and say that's the oldest one, throw it up. Okay, so that's something that you'll keep in the PCB. That's in the that OS will track separately. This is just what the process is doing. Okay, the OS is also in memory, which we are not showing here. Okay, so you will have to keep that information. At the moment, we are doing it in our heads. Okay, but the OS in reality will have to keep track of when each page was brought in. And you'll have to use timestamps and do these things. Okay, so we were at D. Okay, that's a page fault. Okay, you threw out A. Now next axis is A, which you just threw out. So that's another page fault. Okay, so you look at D, B, and C. Say what's the oldest page? Oldest page is B. Okay, because B was brought in here, C here, and D here. So I'm going to make that D, A, C. Okay, so we are here. So that was a page fault. You access D, D is still in memory, no page fault. B, page fault because you threw it out. Okay. So now D, A, and C, you say which is the oldest page? C. Okay, so this is going to go out. So D, A, B. Okay, then you basically, that's a page fault. Then C is another page fault you are going to throw out. In this case D, because A was brought in here and B was brought in here. So D goes out, C comes in, so this becomes C, A, B. That's a page fault. And then the last axis is B, which is already in memory, no page fault. Right? So you fill this up, then you count the number of page faults, and you'll see there are 6 or 7. Okay. So that's basically what happens for FIFO. We are going to do the same thing for LRU next, or that min and then LRU. Okay. Okay, so min is same reference stream, but now we are going to look in the future. I should erase this. Okay, just to speed this up a little bit, the first 3 axes is you start with empty memory. First 3 axes always page fault. There's nothing to replace this empty RAM, so you'll basically have the same problem regardless of what algorithm is until memory fills up. Okay. So that's your A, B, C here. Okay. First 3 are page faults, then you access A, it's in memory, no page fault. You access B, it's also in memory. Okay. A, B, and C are in memory, not a page fault. Then you access D. Okay. Like before, that's a page fault because D is not in memory. Okay. Now you have to peek into the future. Okay, and say what's the page I want to throw out from A, B, and C. Okay. You want to throw the page that's accessed the farthest in the future. So you look at, we are here, so look at the future. So A is accessed 1 time step from now. Okay. B is accessed 3 time steps from now, and C is accessed 4 time steps from now. So C is the page that's going to be accessed farthest in the future. Okay. So you're going to throw out C. Okay, so what you will have at this point is A, B, and D. Okay, so at this point you have A, B, and D. Okay, because you looked into the future. Okay, so now next axis is A, it's still in memory. B still in memory, D still in memory, B still in memory. Okay, you could look in the future, so you know actually that's what the next page fault is going to be. Okay, so you access C, that's a page fault. Now you have limited history, so the only thing you should do is not throw out B, but you can throw out one of the other 2. Okay. So you will see that the number of page faults dropped. In the previous case, there were 7 or so. Here, you have come down to 5 or 6, okay, because you actually looked at the future and reduced what the number of page faults you would incur will be. Okay, but now what you should realize is this is not given to you. Okay, this is because typically not given to you, meaning the OS doesn't know what the reference stream is. You find out, you only know what has happened until this point. You typically don't know what's happening in the future. Okay, so you can never really implement this. In this case, we were given what the reference stream was, so we could compute this. Okay, but in reality, what you will have is if this is the current time, you will know what has happened in the past. But this will be blank. You don't know what's happening in the future. Okay. Next up is LRU. Okay, you will do the same thing as we did for min, but we are going to look at the past and throw the page that was accessed the farthest in the past. Not necessarily brought in the farthest, but accessed farthest in the past. Okay. So these three are all like usual page faults. Okay, so at this point you have brought in A, B, C. Okay, you access A, still in memory. You access B, still in memory. Then you access D. Okay, that's a page fault. Now you are going to be here. You are going to look at the past and say of A, B, and C that are in memory, which was accessed the farthest in the past. You say B was accessed 1 time step ago, A was accessed 2 times steps ago, and C was accessed 3 times steps back. C is the least recently used page of these three. Right? So that's why you evict it. That's why it's called LRU, or least recently used. Okay? So C goes out, D comes in. Okay? In this case, it turns out to be a good bet, because if you look at the future, that's what actually happened in the future as well. But LRU is not perfect. It is going to make mistake, because the past is never a perfect predictor of the future. It's approximately what is going to happen. In this case, you are lucky. Okay? So you bring in D. Okay? So now you have A, B, and D. So A is in memory, D is in memory, B is in memory, C is again a page fault. Okay? So now you have A, D, and B. You look in the past and say, what's the least recently used page? B is accessed here, 1 time step back. B, D, and A. So A is the least recently used. So that's the one that goes out. Okay? And then C comes in. Okay? B is not a page fault because B is still in memory. Okay? So in this case, LRU is matching min because we lucked out. Okay? But it will approximately match min. It will have slightly higher page fault rate in practice than min, because you now don't have perfect knowledge of the future. Okay? Past is never a perfect predictor. It's an approximation. But in this example, it's the same. You get the same number of page faults. Any questions here? Yes.
Randomly, random page replacement are used in practice.
Can you speak up?
Random page replacement are used in practice.
Random page replacement ever used in practice? So the question is, why not pick at random? Okay? From an implementation standpoint, that's the most attractive, because there is no bookkeeping to perform at all. Okay? Page one needs to come in, pick a page at random and throw. It surprisingly performs well. Okay? Not as good necessarily as min, because you cannot do as well. But if you have a large number of pages, if you randomly throw a page, the chances that the pages you are throwing out are immediately accessed are small from a large set. Okay? So you may make probabilistically smaller and smaller mistakes. Okay? So it is not used in practice, but techniques have shown that it does quite well. Okay? LRU is what is typically used, but random does roughly as well if you look at how it actually behaves. Okay? Unfortunately, we can't do random here, because you can pick whatever you want and different times you'll get different results, but in overall it does well. Okay. So now I'm going to show you some bad cases for LRU. Here's a case where LRU is going to make a lot of mistakes. Okay. So ABC page faults, okay, same as before. Okay. And then you have B is not a page fault. Okay, so A and B are not page fault, but D is again a page fault. Okay, now you look at the least recently accessed page, that is in this case happens to be C. Okay, so you throw out C, you access A, okay, which is here, you access D, that's here.
This isn't the bad one.
This is the one we did.
Sorry, A, B, and C are in here. You access A, B, and D. Okay, so that's a page fault. Yes.
That's the same stream we did.
Okay, so I think something, maybe I made a mistake. So I'll construct this example here instead of there, because I think that is not showing, should be A, B, C, D, not A, B, C, D. So here is the stream that is going to give you bad performance. So if you just cycle between A, B, C, D in this order, and your 3 pages, not 4, okay, you'll march this way. Okay, and so this is a page fault, that's a page fault, that's a page fault. Okay, you bring D in. Okay, you see which is the least recently accessed page, that happens to be A. Okay, so you are going to evict A. So now here you have D, B, and C. Okay, that next one is A. Okay, that's a page fault. So now you evict B. Okay, so now you have D, A, C. So A came, B went out, A came in. Then you access B. So whatever you are evicting is the next page you access. Okay, so if you are essentially in a think of it, you are in a for loop, okay, and you are accessing 4 pages. Okay, the last page evicts the first page, but you cycle back and you access that next. So you'll keep evicting the oldest page, and as a result, every access here will be a page. Okay. The point here is if this is the working set consists of 4 pages and you gave the process only 3 pages, you are going to have a large number of page faults. This is not a problem of LRU, it's simply saying that these are the 4 pages that are being accessed over and over again, and you gave the process too little memory. So in this very bad case, the page that is going out is the very page that's being accessed next. Okay, so the way you get around this is you simply, if you increase the number of pages by 1, you give the process 4 pages instead of 3, then you will see after the first 4 accesses there are no page faults. The process is happy because you gave it enough pages to hold its working set. Those are the pages you are working on. Okay? So this bad corner case also shows you, okay, that if you give a process too few pages, it doesn't matter what the memory cache replacement or the page replacement algorithm is, you will have a lot of page faults. Okay? In this case, LRU got tripped up because we could construct this scenario where you are basically evicting the page that is getting access next in every step. Okay, so every access becomes a page fault. That's a degenerate case. Okay. All right. So that's LRU, and that's basically saying that you have to give the process enough RAM to hold its working set. Okay? That's true for any algorithm, including LRU. And now we go back to FIFO, and we are going to study the case where you have that access or reference stream, and we'll look at 2 cases. Think of these as 2 tables. First, you give the process 3 frames. Then you give the process 4 frames, and you compare the number of page faults. Okay? Generally speaking, when you give a process more memory, what should happen to the number of page faults? It should reduce. You give it more memory, you can hold more pages. If you can hold more pages, you should typically see fewer page faults. Okay, so we are going to look at this for LRU, or not LRU. Look at it for FIFO first, and then we'll look at it for LRU. Okay. So first we do the example with 3 pages. Okay. So A comes in. I need to write this down. I should have filled it up. Okay. So we have A page fault, B page fault, C page fault. Okay. D also page fault. You have 3 frames, so you throw out the oldest page, which is A. Okay, so D is a page fault. Okay, then that we are here. Okay, then you step 1, you are looking at A, again a page fault, which is the one you throw out now. D, B, and C, what's the oldest? It's B. So you have D, B, C. So page fault. Next is B. That's also page fault. Right. Then you have E. E is not in memory. That's a page fault. So the oldest of this is. So you have E, A, B. It's a page fault. Okay. So now you are here. Okay. Memory contents are E, A, B. A is not a page fault. B is not a page fault. These 2 are not page faults. C is a page fault. There's no C. So of E, A, and B, which one would you throw out? You will throw this one out. Okay. So you have 2 E, C, B. Okay. What's next? Okay, so we are here. So you have D and E. Okay. So you will basically, D is a page fault, okay, which is the oldest page here. E was brought in here, C was brought in here, B is brought in there. Right? B is the oldest one. So C, B, page fault, and the last one is not a page fault. Okay, so now that's the scenario with 3 pages. Okay, let's do what happens with 4. Is that clear? Any questions here? Just work to the reference stream. So here, same scenario. We have 4. Okay, first 4 are page faults. Okay, but you have 4 frames to play. Okay, so we are here. Okay, A is not a page fault, B is not a page fault, E is a page fault. Okay, so E is a page fault, so which is the oldest page here? A is the oldest page. E. Okay, so what happens next? A is a page fault. We just evicted A. And the oldest page is B. So now you have E, A, C, D. Right? Next up is B, that's also a page fault. A, B, D. Okay, so you brought in B. Next is C, also page fault. Okay. You have D, that's also page fault. Okay, so now if you bring in D, you'll see that that's D, A, B, C, and then you have just evicted E, that's a page fault. Okay. So what is this saying? If you compare the number of page faults, which one has more?
The 4 frames.
Okay, so you'll see that this scenario has more page fault than that scenario, because here you had 3 hits, here you have only 2. Everything else is a page fault. So the number of page faults went up by 1. Okay. So what does this tell us? Okay, so memory didn't help. This is completely counterintuitive to what we had expected. We gave the process more memory, trying to help it, and it actually did worse. That's not what you expect. If you give more resources, it should do better, not worse. Yes.
Is this true using history, or is this just for random streams?
Okay, so question is this true for history? It's only true for this example. All right. It's not going to happen frequently. Okay, and it's not going to happen for many algorithms. It's true for FIFO. Okay, so this observation is referred to as Belledy's anomaly. Okay, named after Les Belledy, who discovered it first, saying here's a simple algorithm. You increase the number of pages you give to a process, and it's doing worse. Okay, that's completely counterintuitive. It's an anomaly. Shouldn't be happening at all. Okay. Now this is true for certain types of page replacement algorithms, of which FIFO is one of them. There are others. Okay. So those techniques actually don't necessarily do better if you give them more memory. Okay. Sometimes they end up doing worse. Okay. So these are cache replacement algorithms to clearly avoid, because it is basically going to do not what you expect it to do in some cases. OS trying to help the process and it starts doing worse. OS doesn't know what to do. Okay, should it take away or give it even more? Okay, you cannot tell. Okay. So these kinds of algorithms that suffer from Belledy's anomaly should never be implemented in practice, because they will have all these bad behaviors. Okay, completely counterintuitive, anomalous behaviors. Okay. If you do this for LRU, you will see that that will not suffer from Belledy's anomaly. Okay. LRU doesn't actually suffer. LRU gets monotonically better. It will do as well as it did with fewer frames, but probably better, but not worse. Okay, which is what you expect. That if you give more resources, maybe performance doesn't improve, but it shouldn't get worse. Okay. LRU is in that class. Okay. But FIFO is not. FIFO suffers from this bad case. where things just seem to tank when you try to do something better for the process. So I'm not going to go through the whole thing, but if you work through it, you will see that you actually end up doing better. The number of page faults reduces in this case, not gets worse. Okay? Now the general principle why it does better is if you look at memory contents here, okay? If you take any point in time, okay, and look at the memory content with 3 frames and with 4 frames, you will see that there is basically some pages are overlapping, but there is some random other pages that are shown up. So instead of E, A, B, you have E, B, C, D. A and B are not present here. A and B seem to have disappeared, and B, C, and D. So in FIFO, because you're throwing the oldest page, the contents of memory that you see with as you increase the number of pages could be completely different. Okay? There may be only a few pages that are overlapping, but then you have some pages that are not there when you had 3 frames. Okay? In LRU, what you will see is as you make the pages bigger, this is always a superset. What this means is when you make the memory bigger, all the pages that were here are still here, but there are some more pages, a strict superset. That's a property because of the way you're looking at the past and throwing away pages. You can make that observation. If you actually work through this example and you look at any time step, look at what's there in the memory with 3 frames and 4 frames. With 4 frames, all the pages that are in 3 frames will still be here, always, and there will be some more pages. Okay? What that says is you cannot do any worse because whatever was there is still there, and there is some more. So you couldn't possibly do worse because if there was no page fault in this case, there will not be a page fault here because the same pages are still there. But the number of page faults can only reduce because some more pages are accommodated in memory. Okay? That's sort of an intuitive explanation of what is happening. So algorithms that guarantee that when you increase the amount of memory, all the pages that were there previously will still be there and some more, will ensure that page faults can only decrease. You cannot make things worse because whatever was there is still there. Yeah, so if there was no page fault previously, there will still not be a page fault now because the same pages are there. But if there was a page fault, there is a chance that the faulting page is now in memory in the additional RAM. Yeah, so you can only make things better. Okay? That's the intuitive explanation. Now I cannot prove this for you, but I can only explain intuitively what's going on. Okay? This is why in well-behaved algorithms like LRU, you give it more memory, it gets progressively better in terms of page fault, which is what you expect. The reason this doesn't help have that scenario on LRU is if you look at the memory content, they seem to be completely different. There is no correlation between here and here, so you have some random other set of pages you don't show. Okay? And the reason is you are not looking at the access pattern. You are simply throwing out the oldest page without regard to when it was accessed. Just because a page is old doesn't mean it's useless. It may still be actively used. Okay? What you want is to throw out pages that are not being used. It doesn't matter when they were brought in. Okay? You want to throw out pages that are not used. Okay? LRU has that behavior. FIFO does not. Okay? Which is why you get into these bad situations. Okay? So, and when you think of implementing a page replacement algorithm, it's good to ensure or verify, not ensure, verify that the cache replacement doesn't have penalties announced, because then the OS will be left second guessing what to do. Okay? Thankfully, most algorithms like LRU don't have that problem. Okay? Alright, so now we are going to come to that question that was asked earlier, saying if this is a good algorithm, it's practical, how do you implement it? What do we need to do? What bookkeeping should we sort of have in the system to keep track of which is the least recently used page? Okay, so let's say you are given LR, you say go implement this. Okay, what information would you keep with each page of a process? Yes.
If you wanted to keep a piece of information with each frame, then you could keep how long it's been since it's been used.
Okay, so you try to keep track of how long has it been since it was used. What information would you need to keep exactly to keep that?
The timestamp.
Timestamp, yeah. Okay, timestamp of access, not timestamp when you have brought it. Every time you touch a page, okay, you update the timestamp. I touched this page at this time t. Okay, so you will say this was accessed at this time, this time, this time. So you keep, for every page, you keep the last time it was accessed. So you touch a page, you update its timestamp to the current time. That's the time it was accessed. Okay? Now you want to throw out a page, you look at the timestamps and you say which is the one with the oldest timestamp. That's the one that was least recently accessed, and you throw it out. Okay? So that's a simple way of implementing LRU, is for every page frame, you keep a timestamp of access. Update the timestamp every time you touch a page. So that seems straightforward. Okay, now let's try to analyze the performance of this simple LRU scheme. Okay, so yes.
It's 4 because every time that you want to access a piece of memory, you need to go through the entire list of every piece of memory.
Okay, so first we'll analyze it in two ways. Okay, so you are pointing out something that is the next step. So first is what is the cost of access updating a timestamp, and then second is how efficient is it to throw out a page, because you have to compare timestamps and find the oldest. So these are two operations we will think about performance issues. Okay, so what's the cost of updating a timestamp? So let's say you access page D. I need to go update a timestamp. Okay, what is the cost of that? Yes.
Constant.
Okay, it is constant, that's true. But you have to ask, yes, we have something to add.
Yeah, it's also like really cheap because you're just reading this location.
Okay, so you're saying it's cheap because you're looking at a page and you're updating its timestamp. Okay? Now, let's think about, you should have said where is the timestamp stored, first of all. Okay, typically you won't store it with the page, you will store it somewhere else. Okay? Let's say you store it in the page table. That's the reasonable place to put it. Okay, there's a page table, you go and put it there. Okay? So now every time any instruction touches the page, you are going to go and update its timestamp in the page table. Okay, is that good or bad? Yes. Good. Okay. Okay, so you're saying the page table needs to be checked anyway. So let's just update the timestamp while we are at it. Okay? But do keep in mind that we had a TLB. Okay? The TLB was trying to, we said putting the page table in memory is bad for performance because every memory address access becomes two memory accesses. First you access the page table, then you access the page itself. And we said, so we don't want to have factor of 2 slowdown. We don't want sort of half the speed of what the CPU is capable. So we put a TLB. We said, let's put the page table entries in the TLB. Now we are saying the page table entry is in the TLB, but the timestamp is in the page table. So even if you could look up the TLB, I need to go update the access time. I have to go back to the page table. So for every memory access, if I have to now go update a timestamp, and the timestamp is in memory, then I have again slowed down my performance by factor of 2. Right? So it is very simple scheme. It says, hey, let's just keep timestamp and let's keep updating it. Turns out to be a very bad from a performance standpoint because it is significantly slowed down performance. Every instruction, think about this, every instruction, which almost every instruction touches memory, requires another memory access to update do some bookkeeping for that page. Okay, which you simply cannot deal with. I mean, that is just not going to cut it from a performance standpoint. So this simple straightforward policy will not typically be practical unless you care about performance or unless you don't care about performance. So if you care about performance, you have to do something better than this. So you're going to say, I will not be able to keep your timestamps in the page table at least. You have to keep some timestamp somewhere. Okay, the idea of keeping some timestamp is the valid one. The question is where do you keep it so that it is efficient. Okay, keeping it in the page table, not a good idea. Okay, you basically is going to suffer because of this. Okay, so what else might we do? Okay, this is where I think all of this implementation issues come up. So this is essentially what we said. So that's the keeping the timestamp. Now there is also the eviction part. Okay, the eviction part says, let's assume you have timestamps for pages, but now you want to bring in a page and throw out some other page. how do you decide what is the least recently accessed page? You could just do linear search saying what is the oldest timestamp. Okay, so if you have n pages, you may have order n algorithm. Okay, you basically just look through the entire list and find the oldest page. Okay, is that efficient? Okay, what's better? If you want the oldest timestamp, what is better than doing linear search? Yeah.
Can I store like a queue?
Okay, you can store a queue, but the queue has to be sorted. Right, so basically, you can store it. So you have to, if you store the pages in sorted order in some list, then eviction will be constant time if the head of the list is the least recently accessed page, or rather the tail of the list, the least recently accessed. So you have to keep a LRU list in sorted order, in timestamp order. So every time a page is accessed, you pull it out from wherever it is and you bring it to the head of the list. Okay, so what is at the front of the list is the most recently accessed page. What is at the end of the list is the least recently accessed page. Okay? So anytime you touch a page, you bring it to the front. Okay? So you want to evict a page, go to the end and just throw out the page and bring a new one. Okay? This says now you keep a data structure where pages are kept in a linked list, okay? In particular a doubly linked list. Okay, so you have to bring. So now you can ask what's the performance of keeping a doubly linked list of pages. Yes.
Wouldn't this be the same problem? Because you
Yes. The question is it the point being made is, isn't it the same problem as the timestamp? Yes, because the linked list has to be kept somewhere. It is going to be kept in the kernel address space, in the process control block. Okay? In fact, it is going to be significantly worse than the timestamp because you are manipulating pointers in a linked list. If you know anything about a doubly linked list, you will know that you have to update 4 pointers every time you move an entry. That's 4 memory accesses. Okay, there are 4 pointers that have to be changed, right? So you have a doubly linked list. So let's say that's a page. Okay, here are pages. Okay. If you want to take this page and move it somewhere else, this pointer has to go be updated here, that pointer this way, and then so on. Okay, and then this pointer here you have to update things as well. Okay. So that's multiple memory accesses just to execute one instruction that touched the page. Okay, now you're going to see factor of 6 or 7 slowdown, not factor of 2s.
Why does it have to be doubly linked? Couldn't it be singly linked?
Could it be singly linked? It could be singly linked, but if it is singly linked, then you don't know where the tail is.
Right,
You
but
either
what do
know
you
the
need
head
the
or
tail
the
for?
tail. So let's say it's this way.
Yeah.
Let's say it's this way.
Okay.
Alright, so now if you want to bring this, so you have to actually go through this to find it. Because you know this is pointing here, but you don't know what's the one before it. Let's say you touch this page, you want to remove it from the list and bring it here.
Right.
Okay. So how do you know what's the entry behind it? You only know this page is pointing here. So you have to actually scan the list from the beginning to find this, so that you understand what
But
I'm
aren't you
saying.
scanning from the beginning to find the one that you're looking for anyways?
No, because this you can actually, you access this page.
You can access it directly, you don't need to go through the list to find it.
If you need to go through the list, then you are basically saying to find the page, in order to update it, I have to have even more memory accesses.
Okay, and you don't need to do that.
So I think no matter what you do, if you keep increasing the number of memory accesses per instruction, you are going to have significant slowdowns. Okay?
Okay.
So all the straightforward things we know, which is let's keep timestamp, let's keep it in a sorted queue, let's make it doubly linked, none of that will work here. Okay? Because we are talking about instructions. Each instruction is just doing one memory access. And to do this bookkeeping, if you have n memory accesses, that's going to have factor of n slowdown. No matter what you do, you could scan the list, sure. But then if this is somewhere in the middle and you have 10,000 pages, you have 10,000 memory accesses just to get here.
Alright, I just didn't know you could access it directly.
Yes, so
Okay.
you may have a hash table which will point here and then you have to update. But even that is not good enough. Okay, you are basically saying for one memory access, if even one more memory access is a factor of 2 slowdown. Any other bookkeeping is just going to tank performance even more badly. Okay, so all that it should tell you is LRU, even though it looks like a simple policy, it looks like there are straightforward ways to implement something that says keep track of access times. Implementing it becomes really hard because of these kinds of problems. Okay, so here's a non-trivial problem. Yeah, so what we will look at is so most operating systems will not actually implement what is called pure LRU because it's simply too expensive. No matter what you do, you're going to have very bad performance because the bookkeeping overhead is simply too large. Okay? So what you will do instead is basically do some approximations of LRU. Okay? You will not keep exact timestamps. You will basically keep some coarse timestamps. You will try to implement some coarse approximation that's good enough. Okay, that's basically all that you can afford to implement. You like to do better, but it's too expensive unless there's hardware support. Okay, so we are assuming there's no real hardware support here for us. So we are basically stuck with doing this bookkeeping in memory. Okay, so I'm going to give you, since we are going to run out of time and I need to talk about the lab, just give you a peek at what an efficient implementation is. Okay, and then we'll leave it at that. So I'm going to show you two implementations. One is we'll use a n-bit clock, not a real timestamp, but some n-bit. Let's say n is 2 bits. Okay, so we'll use a 2-bit timestamp. Okay, so if you use 2-bit timestamp, then all the pages will have one of 4 timestamps. Okay, the timestamp will be 00, 01, 10, and 11. Okay. So those are, if you're 2 bits, they can only have these values. If you are 2-bit timestamp, every page has these timestamps. Okay. And the way you are going to update this timestamp is if you access a page, you will basically set its left timestamp to 1. So this goes from 00 to 01. After some period of time, let's say every minute, all the timestamps are left shifted. So whatever was 01 will become 10. If there was 11, that will become 10, 01, and so on. So you just do a shift by 1. So what this is saying is you take time and you just chop. In this case, you're taking time and you partition it into 4 intervals. Rather than looking at per instruction what's happening, let's have 4 buckets. Let's say I'm just making something up. Let's see, the first bucket is what happened in the past 1 minute. Then the next bucket is what happened in the past 5 minutes, what happened in the past 10 minutes, and what's happened before that. I'm just making up some value. Or you could say, so you take time and you just chop it up into 4 intervals and assume that each timestamp represents one of those intervals. This is the newest interval, this is the oldest interval. Okay. So in this coarse approximation, what happens is if you want to do LRU, you will take the least recently used timestamp, which is 00. This is the least timestamp. Okay, this is integer value 1, that's integer value 4 or 3. Okay, so you will pick any page with this timestamp and you will evict it. Okay? You won't know exactly what is the least recently used pages, but you will say this is the group of pages, all of which were accessed the least recently. I don't know which one is exactly the one that is the least recently used, but any one of those will do. That's the approximation because I don't know exactly which one. I'm going to say I'll pick from that group at random and throw one of those ones. Okay, because it's too expensive to implement a real clock. Okay? 2 bits you can probably stick in the TLB. And you're adding 2 bits to a TLB. That's not too expensive. So whenever you do TLB lookups, you can add a timestamp to the TLB. Okay, putting an entire integer, a clock is actually an integer value in the TLB is expensive. That will increase the size of the TLB. Okay, probably double it. Okay? But adding a bit or 2 is okay. So you can implement this scheme in the TLB, and TLB is fast, so we are okay with it. Okay, so now you don't need to keep timestamps in the page table in memory. You can just put it in the TLB. That's as fast as you can make this. Okay, so you keep some small number of bits in the TLB, and you use that as a coarse-grained timestamp. Okay? And so you don't know the exact time. You just basically have buckets saying all the pages in this bucket or access the farther sort of least recently accessed pages. I don't know which one is really the least recent, but we'll treat them as identical. These are all the most recently accessed pages. We don't know which one is which, but we'll just group them and treat them identically. Okay? That's how it works. Okay, so now operating systems don't even keep 2 bits; they just make do with 1. Okay, so what we will see next is actually, which is next time on Wednesday, is an LRU implementation that uses a 1-bit clock. Okay? The timestamp is either 0 or 1. 1 means pages that were accessed recently. 0 means pages that were not accessed recently. So you just have 2 groups of pages: recently used, not recently used. So you say anything in the last 5 minutes, recently used. Every 5 minutes you go and zero everything out. So they become sort of the old pages, and then you keep updating this way. So now you want to evict something, you just pick one from the bit 0 and you throw it. Doesn't matter which one. Okay, that's what we are going to do. So it's a really coarse implementation of LRU where our access time, instead of really using a clock, is a 1-bit clock. It's either 0 or 1. 1 says recent, 0 says not recent. That's it. Okay. That you can implement efficiently, but it's still very coarse grained. We'll talk about that next time. Okay. I want to spend like a few minutes talking about the lab, which is out. There was no discussion this Friday, so we'll discuss the lab this Friday. But just to give you a sense of what the lab is about, so here you need to use threads and synchronization. Okay, this is Java code, so you can use your standard Java threads, and you can use synchronization. The problem is to implement producers and consumers using bounded buffer. We did bounded buffer producers and consumers in class, if you remember. Okay, producers produce data item, they put it into a buffer. Consumers consume data items. Okay, so we are going to use that producer-consumer scenario. The code was actually in the lecture notes, so just look at that and implement something similar. And the problem we are going to solve with producer-consumer is this thing called MapReduce. Okay, it's a data processing framework that is used to produce analyze lots of data. So we are going to implement a toy version of MapReduce in this problem. Okay, the problem is as follows. Okay, so you are given, first I'll describe the problem in abstract and then we'll look at the producer-consumer version. So you're given some files which have text. Okay, so you're supposed to analyze this text in parallel, because there are lots of files, and construct an index over these files. Okay? The index is basically a list of words which appear in the text with a list of where the words appear. So if this let's say word is test, you say it appeared in file 1 on line X, in file 2 on line Y, and so on. So for each word that appears in any of those files, you will construct an index, and the index will simply tell you which files it appears in. Okay? This is referred to as an inverted index. If you remember inverted page tables, I said you will look at inverted indices soon. This is simply a hash table. Okay? You're given a word, you hash into this table, it tells you where what files the word appears. This is what you're supposed to construct. Okay? The trivial way to construct it is write a single threaded program that opens file 1, reads each word and inserts it into the hash table with the line number. Read file 2, okay, and then insert it into the hash table and so on. That's a sequential way of converting this index. Okay. We are going to parallelize it, make it concurrent by making it multi-threaded. Okay. So what we will do is we will have, okay, that's like these are files. Okay. We have some producer threads. Each producer thread is going to read a file in parallel. Okay. And then there are consumer threads. So these are called map threads. This is a reduced thread. Okay, so reduced thread or consumer thread. So after you read each word, you are going to hash on the word and send it to one of the threads. Okay, so let's say you read something and then you send it to this. So the hash will basically say this is the thread to send it to. Okay, so if there are m of these threads, take a word, make a hashing function that hashes the word to a number from 0 to m-1 and send it to that thread. Okay? Each thread has a bounded buffer. So what you mean by sending it is you take the word and you insert it into the bounded buffer. Saying I found this word in this, and then this thread, you may read this and put it here, saying I found this word and put it in the thread. Right? So now all these threads are doing is they're basically converting, taking words from here and making a hash table, which is your inverted index for those words. Okay? Because the hash function is the same, if the same word appears in multiple files, you will still send it to the same thread because it will map onto the thread ID. Am I making any sense or not? Yes, question.
Could you explain thread ID?
Okay. What, explain the thread ID. So let's assume that you have M of these. Okay. So now in order to convert the hash table, whenever a word appears in any of the files, you have to send it to the same thread so it can always send it to one thread only. Okay? The way you are going to do this is, let's say you found a word test. Okay? So what you will do is you will say hash test. And this hash function should produce a number from 0 to m minus 1. Okay? Find any, can use any hash function. So that hash function will take a string and basically map it onto a value from 0 to m minus 1. So let's say this becomes I. This hash function returns I. So that then you basically take test and insert it into thread I's bounded buffer. So if the same test appears somewhere else, you will again hash it, it will get I, so you will again be sent here. Okay? So the same word is always sent to the same thread, always. Okay? Then all these consumers are doing is simply pulling things out and putting it into an inverted index, which is a hash table. Okay, so now you have a hash table for all the words that are sent to you by the mappers. Okay, so here you are reading, the producers are reading the files in parallel, and then they are sending the words that they are reading to the consumers, and by inserting it into a bounded buffer, consumers are converting it into a hash table. And that's it. At the end of this, you just print a hash table. So you completely parallelize the sequential task. The sequential task was you would read file 1, insert all the words into hash table, read file 2, insert into a hash table, and so on. Here your parallel reads and your smaller hash tables being constructed, one per thread. Okay? So you take all the words in this and you will chop it up into smaller pieces and send it to these threads. Okay? So this is parallel data processing. Next question.
Inverted index, does that mean we have to print it in some order?
So inverted index, you can just simply use standard hash tables as is specified in the specification. You don't have to make your inverted index. Use any Java data structure that allows you to construct an inverted, specifically hash tables. Okay? The part that you're going to worry about is the producer, consumer, and the synchronization. Okay? Reading and converting this is the easy part. You just pick a standard data structure and use it. Okay? Nothing earth-shattering there. So long as you know how to insert something into a hash table, you are done. Use some library or an object class to do it. Okay? The part where you parallelize is you will be told how many map threads and how many reduced threads. You have to create that many threads, set up the bounded buffers for each of the reduced, have locks, not locks, semaphores or monitors for each of these, so that when you insert and you take out your synchronization, that's the part you need to worry about. That's what we did here. The rest of it is actually standard stuff. Okay. Now I should mention that this inverted index is what search engines construct. Okay. That's how they grab web pages and index. So when you type a search query, you're told this is the file that matches it. Okay. So you get a list of results. So it's something you'll learn what an inverted index is. So let's stop here.